So SHM of a system about its center of mass. So the typical system that I'm talking about is something like this. On a smooth horizontal surface, say we have a combination of two blocks which are attached by a spring. And now this combination can do SHM in various different situations. For example, the simplest situation we can think of is one where the system is at rest initially and the two blocks are given a push such that the spring is initially compressed by a certain amount and then they are released from rest. So let's take a case like this, that initially we were applying force from both the sides such that the system was at rest. So the spring was in some kind of a compressed state. This. So given, suppose masses are 6 kilograms and 3 kilograms, and the spring constant is, let us say, 8 newtons per centimeter. Now, initially, forces of magnitude, let us say, 24 newtons are applied as shown. And the system is in rest and equilibrium. Now, at t equal to 0, both forces are simultaneously withdrawn. So first of all, we will show that both blocks perform SHM with respect to the center of mass of the system. Then find amplitudes and time period of each block's SHM. Then what we'll do is we'll find x as a function of time, where x is the compression of the spring. So let's get started with this question. So start with the first part and try to understand why each of the blocks, the moment we withdraw the external force, the system sets itself into motion. So first of all, understand what type of motion the system will have, what will be happening to the center of mass, what will happen to each of the blocks with respect to the center of mass. So from that, you can figure out that they satisfy the SHM condition with respect to the center of mass. They will oscillate in harmonic motion. And then by using the initial conditions and all that, we can find out the amplitude, phase constant, and things like that for their individual SHMs. Okay, so probably from your analysis of things like this using work energy and center of mass, you will understand that this system will oscillate in such a way that the center of mass remains stationary, right? And with respect to the stationary center of mass, the spring will keep going from a maximum compression of F by K, which in this case is 3 centimeters, to a maximum extension of 3 centimeters. So the range of motion of the spring totally will be 6 centimeters, from a compression of 3 centimeters to a extension of 3 centimeters. But when in that, like how to calculate the time period and the individual amplitude of the blocks and all that, that is the thing you have to do. So there are a couple of ways we can go about this. So one is a very sort of fundamental method that I understand. Initially, the system is in this state where this is at a compression of x naught. So F is equal to kx naught. From that, I understand that x naught is 3 centimeters. Now I remove the two forces. So the moment I withdraw the two forces, I start my stopwatch. So both the blocks are at rest, but they will race off with accelerations A2 and A1, such that the center of mass remains at rest. So at any instant of time, M1A1 is equal to M2A2. So that acceleration of center of mass is 0. Velocity of center of mass is 0. Displacement of center of mass remains 0 at any instant after this. So if this was my t equal to 0 instant, so after some time, let's say my system has come to this state, okay, where this block has displaced by S1, this block is displaced by S2. The spring is now still compressed, but slightly less compressed. Okay. So there is kx force acting like this. This E1, there is E2. So this is the instant t equal to t. So at time t equal to t, if you look at the block M1, the equation for it is kx is equal to M1A1. If you look at the block M2, kx is equal to M2A2. Okay. Now you can see that x in general is such that x is equal to x naught minus of S1 plus S2. And in general, M1 S1 is equal to M2 S2 because displacement of center of mass is this. Okay. So you can write this equation like this. Now in each of these equations, you can see M1 or rather S1 is to S2 is equal to M2 is to M1. So therefore, S2 can be written as M1 upon M2 S1 and S1 can be written as M2 upon M1 into S2. So we can substitute this here. We can substitute this here. So we'll get the individual equations that This is now going to give us our secondary SHM kind of equation. Okay. A1 is d2 s1 by dt square, and A2 is d2 s2 by dt square. So you can see that d2 s1 by dt square will become minus k into m1 plus m2 upon m1 m2 s1 plus kx naught by m1, and this equation will become d2 s2 by dt square is minus k m1 plus m2 upon m1 m2 s2 plus kx naught upon m2. So this is like, d2 s1 by dt square is minus omega square s1 plus some constant, and this is minus of the same omega square s2 but plus some constant c. These kind of equations we got SHM. Okay. Where omega square is k into m1 plus m2 upon m1 m2. So this term is, for all these types of questions, this term is written like this. It is something called reduced mass. So the inertia of the system works in such a way that it has a reduced mass given by this term m1 into m2 upon m1 plus m2. So from this point onwards, we know that S1 is just going to be equal to some A1 sine omega t plus 5 plus C1 by omega square, and S2 is going to be some A2 sine omega t plus 5, phi 1, let's say, and phi 2, let's say, plus C2 by omega square, that kind of thing. This is SHM of this type.
Can you scroll up?
Yeah, I'll scroll up just a second. Okay, just a moment. So this is, yeah. Okay, this also comes with a minus sign only, with a plus sign. Okay. So this comes with a minus sign here. And this is this. So d2x by dt square is minus omega square x plus c. Okay. So whenever we have this equation, it implies x is of this type. Okay, I'll scroll up. So now that we have come to this standard equation of SHM, the secondary type of SHM equation, which is this one, okay, with the displaced equilibrium point, equilibrium is not at x equal to 0, but at x equal to c by omega square or whatever. Okay. So rest is just, yeah, you wanted to see the question or the solutions first part?
So both.
Both. Okay. So just take down the data of the question here. Yeah, just put it all here. M1 is 6 kg, M2 is 3 kg. Okay. The force we are applying initially is 24 newtons and the spring constant is 8 newtons per centimeter. So this is the data that we'll require. So this is actually more like a question of application of center of mass concept, but a little bit advanced because SHM is put into it.
Yes, you can scroll down.
Okay. So now see, we have reached the equation of SHM in terms of parametric form for each of these, S1 and S2. Now for each of these, I know the value of omega, okay, but I have to find the value of all these, and I know C1 and C2 also. Okay, C1 and C2 and omega are known, but I have to find the amplitudes A1, A2, and the phase constant phi1 and phi2. And from that, I will get the individual SHM equations, and from that, I'll also get x as a function of time. Okay, so this term here, it is called reduced mass for this system. So here you can see that the reduced mass is equal to 6 into 3 divided by 6 plus 3, or 2 kg. And the spring constant is 8 Newton per centimeter or 800 Newtons per meter. So omega square for the system, which is K upon reduced mass, is 400. Okay. So omega is 20 radians per second. Time period is 5 by 10 or approximately 0.314 seconds. So most of the time, in a question like this, you are just asked to find the time period. So we will see that all such systems where the two blocks do SHM about the center of mass, the time period is given by this kind of formula. It involves a reduced mass. It's like a spring mass system, but mass is reduced to M1, M2 divided by M1 plus M. This sort of formula. Yes, Vaishnavi, that's correct. Both of them will have the same time period because they're having same omega square. And we will see that the SHM is kind of synchronized also. Not only they are having the same time period, but both of them go through the mean position at the same time, and they reach the extreme position away from the center of mass at the same time, and the extreme position closest to the center of mass at the same instant. So, you know, they're coming closer and then moving away, coming closer and moving away with respect to the COM. And that happens in a synchronized manner, in the same phase and with the same time period. Okay. So notice that S1 is the displacement of M1 away from the center of mass. And S2 is also the displacement of this block M2 away from the center of mass. So if I get S1 and S2 in phase, okay, then you can understand that synchronization is also happening. Okay. So now you can see that initially, okay, we will take the value of at t equal to 0. Okay. S1 should be 0. So A1 sine phi 1 plus C1 by omega square should be 0. And it starts from rest. So V1 should be 0. So A1 omega cos phi 1 should be 0. Okay. And same for this also. At t equal to 0, S2 should be 0. This implies A2 sine phi 2 plus C2 by omega square should be 0. And V2 is equal to 0. So that implies that A2 omega cos phi 2 is 0. So now see this initial condition set, what it tells me that cos phi is 0 and sin phi is negative. That means minus phi by 2. Same logic here. Phi 2 is minus phi by 2. Okay. So we'll realize that S1 is A1 sine omega t minus pi by 2 plus C1 by omega square. Okay. And again, also E1 plus C1 by omega square should be 0. Minus, because at t equal to 0, S1 is equal to 0. So A1's value, this amplitude's value, is C1 by omega square. And see what was C1 above. You can see that C1 was Kx0 by M1. Must have written it somewhere. Yeah, this term. And similarly, this term. So Kx0 was the force F. So F by M1 would have given us how much? The force we had applied was 24 newtons and M1 was 6 kg. And omega square we just saw is 400. So 1 by 100 meter. So A1 is coming out to be 1 centimeter. I'll tell you a shortcut trick also later to calculate A1 and A2. So from this, we are seeing that S1 as a function of time will actually become like this. It will become A1 into 1 minus cos omega t, where A1 is equal to 1 centimeter, that is Kx0 upon M1 omega square, and omega is equal to 20 radians per second, that is square root of K upon reduced mass. And like this, we will find the equation for the other one also. Be very similar. So apply the same steps over here also and try to get this equation which I'm writing. That you should be getting S2, the displacement of the second one, as A2 1 minus cos omega t, okay, where A2 will come out to be C2 by omega square or Kx0 by M2 omega square, which will come out to be 2 centimeters. And omega is of course the same. You can see that both of them are synchronized SHMs. So they come closest and then move furthest away from the center of mass in a synchronized kind of manner. So this is a very technical way of solving this problem. Okay, writing all the equations at a fundamental level and mathematically solving them without
So
using
is
any
there
of
any
this
better
symmetric.
method?
Yeah, there's like once we're aware of this concept, now we can apply a number of shortcuts. Like for example, for A1 and A2, we don't need to apply the initial conditions. We can use a shortcut. Okay. But again, the thing is that that shortcut will make sense to you only once you're aware of the fundamentals. Okay. So you must know how to solve this question using this kind of method also, the derivational kind of method. And then we can understand what all shortcuts we can apply to get the quantities quickly.
So can you scroll just a bit?
Yeah. So I'll summarize what we've done here also, but first just make sure that all the equations and terms that we've written are clear. Okay, so now that we've understood this, so see what we can, not only about that, but now we know about the spring also. So we can see that as far as the individual blocks are concerned, their displacement away from the center of mass, from the starting position, when they're actually closest to their center of mass, their displacements away from the center of mass are varying with time like this. That if they started at t equal to 0, from here, so the center of mass will be somewhere here. Okay, so after some time, the center of mass remains where it is, but If this block has moved a certain amount, this block would have moved double the amount because the masses were in that kind of ratio. So this S2 and S1 as functions of time are what we are showing above, that time t. Okay. So 1 minus cos omega t graph is like this. This is 2a1. So this is half a cycle. This is a cycle, okay, where we saw, okay. So omega was 20 radians per second and time period was therefore 0.314 seconds. And therefore this maximum amplitude would be this maximum displacement would be 2 centimeters because E1 was 1 centimeter. Now, if you compare that to S2, you will see S2 has a larger range of motion, right? Because it's a lighter block, so it goes away further compared to S1. Yeah, whatever. So S2 has a range of motion of 4 centimeters. That is 2a2. But it has the same periodicity and it's synchronized. So at 0, both of them start from the closest position. At t by 2, they simultaneously reach the furthest away position. Only difference here is that A2 is 2 centimeters, rest is the same. Okay. So you can see that at t equal to t by 2, the spring has maximum length. That will become L minus 3 centimeters plus 6 centimeters. So it will become L plus 3 centimeters. So maximum extension will be this. Whereas at t equal to 0, the spring has minimum length, L minus x naught. That is. So the range of motion of the spring is from L minus 3 to L plus 3 centimeters. But individually, the blocks are doing SHM with an amplitude of 2 centimeters and 1 centimeter, respectively, okay, for M2 and M1, and a range of motion like this. Okay. So now you can see that x being the compression of the spring at any time, x is equal to x naught minus S1 plus S2. So if you write that numerically, it is equal to 3 centimeters minus of 2 1 minus cos omega t plus 1 minus, actually it's 1 and 2, but anyway, it's one and the same thing actually. So the compression of the spring at any instant of time is, you see that this 3 and 3 cancel out. It will come out to be This is the compression. So this X ranges between 3 centimeters and minus 3 centimeters. So this is maximum compression, and this will become maximum extension. Because if we express the compression as a negative quantity, it means it's become an extension. Okay, so this is overall what is happening to the system. Okay. From here, we'll go about seeing how we can simplify the solution, okay, by using a number of shortcut tricks. And then we will see the same system in other situations, okay, where the center of mass may not be at rest, like it is at rest over here. Then basically with respect to a moving center of mass, the two blocks will be performing SHM, which is also very interesting case. Okay. Now, one thing you notice here that when I've written S1 and S2 as a function of time, I've referenced it as displacement from the starting position. Actually, I've taken it as displacement, not as position with respect to mean position or with respect to the equilibrium point. So I've got this kind of equation. Okay. But I can also do like this, that I can reference it to the mean position of the system. Where you understand the mean position is when the spring is back to natural length. So basically, you can do this question using a sort of hybrid method, that you use center of mass and work energy like you would do for that kind of problem, you know, to find maximum velocity and all those things. And you then put in the idea that, okay, there is SHM also happening over here. Okay. So you can also approach the problem this way, that M1 and M2 are initially in this position where they are compressed like this, and they are setting off with some accelerations, but they are starting from rest. So at this point of time, the kinetic energy of the system is 0. The potential energy of the system is half kx naught square. So the total mechanical energy is half kx naught square. So naturally from here, they come to the natural length position where their speeds will be individually maximum. So you also understand that this is an extreme position of SHM, of their oscillations, because both the blocks are at rest. So kinetic energy is 0 and potential energy is maximum. Now from here, when they come to this position after some time, where they've reached the natural length, in fact, you'll realize that they'll come to this at quarter of a time period, because from extreme position to mean position. Okay. So this is when this will have the maximum speed. Okay. This will have the maximum speed in this direction. So you have all these things that, you know, M1 V1 is equal to M2 V2. Okay. This displacement. Now this displacement will be equal to this one's amplitude. This displacement will be equal to this one's amplitude. Okay. So you have M1 S1 is equal to M2 S2. This is because center of mass is at rest. So you have this thing from here, that M1 A1 is equal to M2 A2. So in this case, you can see that 6 kg into A1 is equal to 3 kg into A2. So A1 is to A2 is 1 is to 2. And you have S1 plus S2 is equal to, I mean, in this case, A1 plus A2 is equal to X naught. So A1 plus A2 is equal to what was our F upon K earlier on. that was 3 centimeters. So you have this statement and this statement. So from this you can easily understand that A1 is 1/3 of x naught, that is 1 centimeters, and A2 is 2/3 of x naught, that is 2 centimeters. That is done. Okay. Now you can also understand one thing very nicely, that to calculate omega you can avoid all that, and you can just understand that this V1 max will be equal to A1 omega, and V2 max is equal to A2 omega. But this is just using from before I should know. It is understood that both blocks have common time period or omega. Knowing that thing, okay. So that's also not too difficult to understand, but okay. So I can calculate omega now like this also, actually, because I can see that half m1 v1 square plus half m2 v2 square plus half kx square at any point of time is half kx naught square. So I have half m1 a1 square plus half m2 a2 square is equal to half kx naught square. So from this actually I can calculate. Now you'll remember that A1 was basically how much it was? M2 upon M1 plus M2 x naught. Okay. And A2 was M1 upon M1 plus M2 x naught. If you just do this from here itself, you'll be able to show that your omega is square root of k divided by reduced mass. So here I'm sort of generally using this relation that A1 is to A2 is M2 is to M1, and A1 plus A2 is x naught. Okay. So A1 is M2 upon M1 plus M2 x naught, which in this case this is 1 is to 2, so this becomes 1/3 of x naught. Okay. And A2 is M1 upon M1 plus M2 x naught, which in this case is 2/3 of x naught. Okay. So I'm using the general terms here, and bit of algebra is still required for this, but so you can see that omega will come out to be this. Okay. And now just the initial condition, then all is required. Okay. So for that, I'll take you to that also, but just make a note of this first. So this is the sort of shortcut method that you can use. Okay. You can see here that basically I'm just sticking to that idea that I know the amplitude for the spring is going to be x naught. Okay, because the spring is not going to compress more than x naught, and the maximum extension is also going to be x naught. I know that from work energy. So I know the sum of the amplitudes A1 plus A2 is going to be x naught. And additionally, I'm using the center of mass concept that M1 A1 is equal to M2 A2. Okay. So A1 is to A2 is M2 is to A1, M2 is to M1. So I know the ratio of their amplitudes for M1 and M2 will become inverse of the ratio of the masses, that is 1 is to 2. So from that I've got A1 and A2. And now I'm again using the work energy trick that when they come to the mean position, the initial potential energy half kx naught square is converted to kinetic energy. And in that kinetic energy, each one of their speeds is omega A1 and omega A2. So from that I can reduce and find the value of omega. So, if I were doing this problem numerically, I would just substitute this directly instead of in terms of M1, M2 and all that. I would write A1 as, 1/3 of x naught and A2 as 2/3 of x naught. and M1 and M2 as 6 kg and 3 kg respectively, K as whatever 8 newtons per centimeter. So directly I'd get the value of omega from there as 20 newtons per centimeter. So 20 radians per second omega. Okay, people. So hope this approach is also clear.
The 2 minutes to note it down.
Okay, okay. Okay, so practice this method later also, just doing it directly numerically. Like I have substituted everything in terms of M1, M2, X0 like that. So just put in the numerical values of M1, M2, X0 and K and write these equations. Okay, so your work energy relation and your center of mass relation, which will give you the ratio of A1 is to A2 is 1 is to 2. Okay, so from that you will see it's quite easy to numerically work out all the parameters. Okay, so this is done, no?
Yes.
So another way you can get that reduced mass thing quite easily is that if you look at the free body diagram of the two blocks, but reference it to the equilibrium position. Don't reference it to the initial position like I've done. So okay, initially this particular system had the maximum compression and all that, but we will not reference our general time t to that. What we'll reference it is to this was at t equal to 0. But we will first take into account this situation. When the blocks are at their mean position. So their acceleration is 0. So this is the mean position. Okay. Now, obviously, to go from here to here, the spring has pushed it. So they've reached some velocities, okay, V1 and V2. So now assume that after some time, they've gone further away from the mean position. So they are now at this kind of situation where this has become L plus X. So this is at again some time t. But all this while the center of mass is remaining stationary. The center of mass is here. Here also it is at the same position. Here also it is remains. So center of mass is at rest. So keeping that in mind, you'll see here that with respect to the mean position, if this block has made a displacement of x1 and this block has made a displacement of x2, so you can see that m1 x1 is equal to m2 x2. In other words, x1 is to x2 is m2 is to m1. And comparing this and this, you can see that x1 plus x2 is equal to x. So from these two equations, again, you get that individual thing that x1 is m2 upon m1 plus m2 x, and x2 is m1 upon m1 plus m2 x. Now from here, it will be quite easy to show the equation of SHM because this is also being pulled by the spring force kx. That is also being pulled. This is having an acceleration a1, this is having an acceleration a2. So now just look at the FBDs in this situation. For this block, kx is equal to m1 a1, okay, where a1 is minus d2 x1 by dt square. And for this block, kx is equal to m2 a2, where a2 is minus of d2 x2 by dt square. So you got the equation of SHM actually. You got that d2 x2 by dt square is minus k by m2 into x, and now from here substitute x. So it is minus k upon m2. So x in terms of x2 is how much? It is m1 plus m2 upon m1 x2. So this is your omega square. And same way, substitute this one here. So you get this, that a1, which is minus d2 x1 by dt square, is k by m1 x, and further x is that. So d2 x1 by dt square is minus k by m1 into m1 plus m2 by m2 x1. Okay. So both these equations are the same. The omega square is the same for both the equations. So from here now you can see that for both the equations, d2 x1 by dt square is minus omega square x1, and d2 x2 by dt square is minus omega square x2, where omega square is this common term. It is k into m1 plus m2 upon m1 m2. So it is k divided by reduced mass. Okay. So x1 is some amplitude into sine omega t plus phi. x2 is some amplitude into sine omega t plus some phi. Okay. And what is happening is that at t equal to 0 now, we have to take x1's initial value as minus of a1. 0, and x2's initial value similarly will be minus of a2, and that's how you'll get x1 and x2 as a function of time, and from that you can get the spring's position as a function of time. So this is yet another way of approaching the question. So basically, this part you can see that at t equal to 0, x of the spring is minus f by k, or minus 3 centimeters. So minus of a1 plus a2 is minus 3 centimeters. So from that you will get a1 and a2 into it. So I'll just leave this for you to browse through once more. So at the moment it might seem a little lengthy and complicated, but if you do 3 or 4 questions, there are some in HC1 also, which are based on this kind of system. You'll get used to this reduced mass formula, and also how to work out the amplitudes from the initial conditions. There are some variations of this situation also, as I was telling you, where the center of mass is moving. So once you look at those also, it will become a very routine thing for you. Okay, so let's look at another version of this question. So, just remember that when we are discussing all this, actually, you're doing a lot of revision of center of mass concepts and work energy concepts and all that also. So don't worry that we are spending a lot of time on just 2 or 3 SHM questions. There's a lot of core mechanics actually, which is happening for you. So, we again have that system only, M1, M2, spring constant. But this time the system is at rest with this thing in equilibrium. I mean, the spring in natural length and both the blocks are at rest. And instead, let's say we have another block coming in and making a collision like this. Okay. So initially at t equal to 0, this is at rest, this is at rest, and the spring is at natural length. Now this given that these blocks are like this is 3 kg, M2 is this time 2 kg, let's say, and the spring constant is 30 newtons per centimeter. Now the third block is of mass 1 kg, let's say, and makes an elastic, though not perfectly elastic. So let's take the value of E as 1/2 head-on collision with M2. So let's start with some normal things here. Find the speed of each of the 3 blocks just after impact. And then we'll find the maximum compression and extension of the spring. And then we'll find the time periods and amplitudes of each block, that is M1 and M2, each block's SHM with respect to their center of mass. This. And one more interesting thing we can do is find the maximum speed, maximum and minimum speed. So this will be a little bit challenging. Maximum and minimum speed of M1 and M2, but not in center of mass frame, in ground frame, anytime after impact. So after impact, that whole system is going towards the left, but with the spring alternately compressing and expanding. So during that strange kind of motion that, the center of mass is moving uniformly, but with respect to center of mass, the blocks are doing SHM. At any point of time, what is the maximum speed and minimum speed of each of these blocks, M1 and M2? So this is like quite a tricky type of question, especially if you try to answer the fourth part, for example, just using center of mass and work by energy method. But if you sort of develop a hybrid method where you are taking into consideration the SHM equations also, you will see that we can really shorten the solution of this quite easily. Okay, so I'm just giving you the results of the collision part first. Okay, so generally I prefer to use these kind of formulae for the collisions. Just show you what I'm going to do. So just before impact, if this guy has a velocity v naught, okay, this is at natural length, this is at rest, this is at rest. So then just after impact, the impact will not result in anything happening to this block. Okay, so this will remain at rest, but this will develop a velocity, which now I will call as, let's say, u2. Okay, so I'll solve it this way, that m2 is given to me as, how much was it now, 2 kg, and m3 was 1 kg. Okay, and coefficient of restitution was 0.5 or half, and also v naught was given in the question. Maybe I have not given v naught, so I'll give a numerical value of v naught also. So might have solved in terms of v naught, but let's take some numerical value of v naught. So v naught is, let's say, 2.4 centimeters per second. So v naught is, let's say, 2.4 centimeters per second. So this velocity that this one will have, u2, this will be like 1 plus e into 2 kg, sorry, into 1 kg divided by 1 plus 2 into 2.4. So it will be 3 by 2 divided by 3, 2.4. It will be 1.2 or b naught by 2 like this. Okay, and this one will have velocity, let's say u3, that will be m1 minus em2. So that is going to be this. I'll actually write this parametrically. Okay, then you can understand it better. Write this parametrically first. Be 1 plus e m3 upon m3 plus m2 into v naught. Okay, that will be this. Similarly, this term parametrically will be this. So in this case, this will work out to be 0. I think. Which you can see agrees with the momentum conservation and all that also. Okay. So you can see that u2 becomes 1.2 centimeters per second. u3 becomes 0. So the separation velocity becomes 1.2, which is half the approach velocity. Okay. And you can also check that momentum conservation is there, so there's no problem. Okay. So once this is over, forget about that third block and all that. Okay. So this is this system's initial state. So this is this system's initial state. That is, so just after impact, what happens is that M1 and M3 both are at rest. And actually M3 remains at rest forever. But M1 will of course gain velocity after some time. And M2 has a speed of 1.2 centimeters per second, or v naught by 2 towards the left. Okay, so from here on, we have to concentrate on the SHM of the two blocks. So from this point onwards, what you do is, from here on, the net external force on the system, on this system, equals to 0. Okay. So the center of mass moves uniformly, okay, with a VCM that is m1 into 0 plus m2 into v0 by 2 divided by m1%. So remember, m1 was 3 kg. So, v0 by 5. Moving towards the left with a constant velocity like this. And while the center of mass is moving uniformly, the two blocks should be performing SHM with respect to the center of mass. So let's try to solve the SHM of the two blocks in the center of mass frame. So center of mass moves at uniform VCM equal to this value towards the left. And in the center of mass frame, blocks M1 and M2 are in SHM. Is what is happening. So get into the center of mass frame and solve their SHM equation. And you can use any of the tricks that we've discussed above and all these things. So one more data we'll need is the spring constant, which was 30 newtons per centimeter.
So this is purely JEE Advanced.
Yes, of course, this is purely JEE Advanced, and that too paragraph type question, okay, where one option will be just finding the time period of the SHM, so that you'll ultimately see is the direct formula using the reduced mass. So omega square for the system will be K divided by reduced mass. So that you can do directly. But for example, finding the individual amplitudes, or if it's a more tricky question, the maximum and minimum speed of the blocks after they start the SHM and all that in the ground frame. So those things become a little bit more tricky. Okay, so now let's come down to this. So let's track how the system is moving from here, from the center of mass frame. Okay, so now let's say we are located at the center of mass. So the velocity of the center of mass we've already seen is 0.48 centimeters per second towards the left like this. So at just after impact, what is happening is this is at natural length, and in the center of mass frame, this block is having some velocity v2, and this block is having some velocity v1. Remember, these v1 and v2 are not in the ground frame; they are with respect to center of mass. So in the ground frame, m1 is actually at rest. So in the center of mass frame, it will have a velocity equal to 0.48 centimeters per second like this, and this one was having a velocity of how much was that? 1.2. So it will be 1.2 minus 0.48. So that is going to be how much? 120 minus 48. So that is going to be 0.72, right? Like this. Okay. So remember here that V1 and V2 are with respect to center of mass. If you compare this diagram to the earlier diagram above, you'll understand how it is different. Okay. So this is at the mean position of SHM. You can see that this is mean position of SHM. Okay. So compared to this now, if after some time they've reached a position like this. So remember, I am in the center of mass frame. So for me, the center of mass is not moving. In this frame, the center of mass is not moving. Okay. So if this block has moved by S1 and this block has moved by S2. So now the spring is compressed by X. So I can even write it as X1 and X2. Write these as X1 and X2. So X1 and X2 are also with respect to center of mass. Okay. So I have M1 X1 is equal to M2 X2, which in this case tells me that X1 is to X2, which in this case will be 2 is to 3. Okay. And X1 plus X2 is equal to X. So again, solving this and this, we'll see that X1 is that same thing, M2 upon M1 plus M2. So you're going to come to that reduced mass formula. When you write the FBD equations, you can see from this that you're going to expect that reduced mass formula. In this case, X1 is 2/5 of X and X2 is 3/5 of X. So at this stage, this is what the force picture is looking like. So this is having an acceleration A1 in this direction. This is having an acceleration A2 in this direction. All this is with respect to center of mass. A1 and A2 are also with respect to center of mass. But in this case, the center of mass frame is actually an inertial frame, because the acceleration of the center of mass is 0 on the ground. So really, we need not worry about all that. Okay. So this one's FBD is showing me that Kx is equal to M1A1. This one's FBD is telling me Kx is equal to M2A2. So I can replace X with M1 plus M2 upon M2 X1 and write this like this. And here also I can reduce this by writing X as M1 plus M2, this time upon M1 into X2 And on the other side, I can replace A2 with d2x2 by dt square. So both of them are giving you your regular SHM equation with reduced mass. d2x1 by dt square is minus omega square x1, okay, and d2x2 by dt square is minus omega square x2, where omega square is k upon reduced mass, where reduced mass is once again m1 m2 upon m1 plus. So this always happens in this type of a system, whether the center of mass is at rest, like in the first example we saw, or the center of mass is moving uniformly, like in this example, or there's a third situation where the center of mass could be moving with acceleration also. But even in that case, though the center of mass frame will become a non-inertial frame, in this case, the center of mass frame is still an inertial frame. So that's why no pseudo force is taken into account. Okay? So x1 is some amplitude into omega t plus some pi 1, and x2 is some amplitude. Now it's very easy to find these amplitudes and phase constants because I know the velocities. No? So this velocity that is there is actually a1 omega because it's the maximum speed, because it's at the mean position. And this velocity that is there, it is a2 omega. So from that I can find a1, a2. I don't even need to apply work energy or anything like that. So that is where the tricks come in over here. Okay? So first of all, let's find omega. Okay. So your reduced mass here will become 3 into 2 divided by 3 plus 2. So 6 by 5 kg. And your K, remember, was 30 Newton per centimeter. So omega square is 30 into 10 raised power 2 divided by 6 by 5. So that's 25 into 10 raised power 2. So omega is 50 radians per second, which was one important thing for us. Okay. Now we can also see that at t equal to 0, that started from mean position. Okay. So x1 was 0. Okay. And x2 0 was 0. Okay. So phi 1 is equal to 0, phi 2 is also equal to 0. And a1 omega was how much? It was 0.48 centimeters per second. So a1 into 50 radians per second. You see, it has a very small amplitude. So this amplitude is like 0.48 divided by 50 in centimeters. Okay. So that is like 0.0096, right? Centimeters. So 0.096. No, 0.0096. Okay. So I can write this in millimeters like this. And again, A2 omega was 0.72 centimeters per second. So maximum compression or extension of the spring will be A1 plus A2. Now we'll discuss a very nice trick to calculate the maximum and minimum speed of each of the blocks in ground frame. It's very easy to analyze the motion of each of the blocks in the center of mass frame. And to analyze the motion in the ground frame, we have to just superimpose the velocity of the center of mass. So by doing that, you can see that you come to a very effective method. Okay, so let us now look at the two sort of extreme position situations. Okay, one is when the blocks are not extreme, but actually mean position situations. When it is like this, and in the center of mass frame, this is coming at A1 omega like this, and this is coming at A2 omega like this. So this was 0.72 centimeters per second, and this was 0.48 centimeters per second. So in ground frame, what is happening over here? In ground frame, okay, the same picture, if I look at it from the ground frame point of view, what is the speed of the block M1? Or rather, what is the velocity of the block M1? This. Okay. So remember, center of mass is moving in this direction with a velocity of, what was the velocity of the center of mass? 0.48. Okay, so this one in the ground frame is at rest. No? So its minimum speed is 0, because every time it's at that mean position where it's coming towards the center of mass at 0.48, it's actually at rest in the ground frame. Whereas this one is having in the ground frame a speed of 1.2 centimeters per second. So this one is at maximum speed in ground frame. And this one is at minimum speed, which is rest in the ground frame. Okay. Now let's look at the other extreme situation. The other extreme is when they've come closest and now they're going further apart. So they are again at the mean position with respect to center of mass. Okay. But this time they're having velocities in this direction. A1 omega 0.48, and this is having in this direction A2 omega 0.72 centimeters per second with respect to center of mass. So in this picture, in the ground frame, what is happening to them? This one is having a velocity in the ground frame of 0.48 plus 0.48, 0.96 centimeters per second. This one is having a velocity in the ground frame of 0.72 minus 0.48. So that's how much? 0.54. So right now, this is having, while the center of mass is moving at 0.48. Okay. So this one is having maximum speed, and that is 0.96. But this is having maximum negative speed. I mean, in opposite direction. So you can see that this one's speed switches direction.
It's 0.24, right?
Which one? This is 0.24. Yeah. Yeah, my mistake. It's 0.24. But the important thing is it switches direction. Okay. So if it switches direction, then that means at some point of time it'll be at rest. So its minimum speed for this block will be 0. Because it switches direction, so it must be coming to rest in between. Okay. So if you think in terms of velocity with sign convention, if you're taking towards the left as positive, then M2's velocity ranges between plus 1.2 and minus 0.24, whereas M1's velocity ranges between 0 and plus 0.96. But if you're just taking speed into account, the minimum speed of M2 will also be 0 at some point of time, because it's switching direction in the ground frame. So this is something which would be very difficult to judge without using the SHM concept. Okay. So if you take this as your x-axis, you can see that the velocity of the first block in the ground frame, it ranges between 0 and 0.96 I cap centimeters per second. But the velocity of this second block in the ground frame this ranges between 1.2 I cap, okay, and minus 0.24 I cap in centimeters per second. So it actually switches direction. It goes back and forth. Whereas M1 never really switches direction. It has a stop, start type of motion. Whereas when you look at them in the center of mass frame, their motion is very simple. They're doing SHM. Okay, so their motion is ranging between extreme position furthest away, extreme position closest, extreme furthest, extreme closest, and going between those extreme positions, they cross the mean position where they have either coming in towards the center of mass A1 omega and A2 omega, or going away from center of mass A1 omega and A2 omega. Okay, people. So this is like a very tricky and important like variation of SHM. So just make sure that you understand that in both these cases, the reduced mass formula applies for time period. So if you are just being asked time period, it's pretty simple. Okay. Or for example, if you're being asked the maximum speed with respect to center of mass, A1 omega and A2 omega. So again, like that. So if using work energy or whatever, you found the maximum compression of the spring, that is your x naught or x maximum, then your A1 plus A2 is equal to that x maximum, and A1 A2's ratio will always come from the inverse ratio of the masses. That is M1 A1 is equal to M2 A2. Okay. Now one more variation of this is there, which I would like you people to try when you are revising today's lecture, and we'll discuss that in the next lecture. If you take the same system, and this time for simplicity, let's take equal masses so that the thing becomes a little easier to handle. So let's take a system with equal masses, okay, and a spring attached like this. Now x is equal to 0 initially, the speeds are 0 initially. It's on a frictionless surface, but we start pulling the system with a constant horizontal force. Okay. So again, we have to show that the blocks perform SHM with respect to the center of mass. Keep in mind that the center of mass will be uniformly accelerated. Okay. And just take some numerical values, like for example, take the mass of each block to be, let's say, 8 kg, and the spring constant to be, let's say, 16 Newton per centimeter, and take this force we are applying as 20 newtons. Okay, so find the amplitudes, time periods, and all these things of the SHM, the maximum extension and compression of the spring, all these things. So try this for homework. We'll discuss in the next lecture. I wanted to discuss this thing, damped oscillation also today. It would have just taken 5-10 minutes, but I have another lecture coming up at 6:15. So we'll conclude here today, and we'll keep the damped oscillation part for the next lecture along with the discussion of this. And after completing this along with damped oscillation, then only we'll start wave mechanics, which is our next topic. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Can you scroll up once and show the 4 diagrams in the previous question? Yes, sir. Done. Thank you, sir.